So, I think I have somebody, nope, nobody turned anything in, so let the hand back to you. Hey, so this is 5th period, right? So just listen up for your name. If this is you, I'd like to have you do this sometime by the end of this week, if possible, if not next week. Okay? Zoe's not here. Liz, you have the graphing quadratic functions. Okay? Sophia Montgomery, graphing quadratic functions unit test, okay?
No.
Oh, that's it.
And then Liz, you have the polynomial equations of factoring, quiz 2. Liz, you have the poly equations of factoring in class test, so you have a little bit more than this for next week. And Elizabeth, graphing quadratic functions, quiz 1. And then, anybody else? So, Liz, I'd say let's try and get at least one of those started by the end of this week.
Okay.
Sound like a deal?
Yeah.
All right. As far as the announcements go, that's done. All right, see you next time. So I just need to let you know that we have roughly 8.5 weeks left of school. So I'd say get your game face on, make sure you're good to go with it. Make sure you're completing your homework, and most of you all are doing that. So most of you should be pretty satisfied by what your grade is. If you are, keep doing what you're doing. I'm not going to change it all that much. As far as this week, we just have lectures. We don't have any quizzes planned this week. Is that okay? I know most of you are pretty upset. You're probably looking forward to all last week while you're at home. I hope I have a quiz next week. I heard there was, oh my gosh, one of the teachers that teaches Algebra 2 with me, they gave their quiz that the kids had missed today. I'm like, dude, that's not nice. I mean, even if we would have missed it, I would have. But what I will do for you is this. You guys ready for a giggle? So let me go through the lecture quick. And then over the next couple days this week, probably get it all done by Friday. Probably the last 10 minutes each class, we'll have the orange story. We'll sum it up. Because we missed out on it. I'm sorry. So, cool? All right. Everyone have notes? Good. All right. So let's talk about, you all know that there's different number systems out there, right? I mean, the ancient Greeks, ancient Mayans, I mean, all the different cultures out there, depending upon what continent you're wanting to deem your history from of mathematics, they all had it. But do you realize that it was the ancient Mayans that actually came up with the theory of zero, of nothing? Okay? The Greeks and the Romans and Pythagoras and all those guys over there, and I guess what would be classified now as the Middle East, when they were doing all their math, they didn't fathom the concept of zero. It's the ancient Mayans up from Central and South America that came up with the concept of nothing, which is kind of cool. So, yeah, the real number system, those are all of the numbers you've ever dealt with. The rational numbers, those are numbers that can be written as fractions. Integers are just like numbers like 1, 2, 3, 4. Irrational numbers are numbers that you can't write as a fraction. And then non-real numbers, that's a whole new idea. And where you start seeing non-real numbers in math is if you had something like that, the square root of -8. If you plug square root of -8 in on most calculators, it's going to give you a message that's going to say error, not real, or not real error in line 24 or something like that. It tells you actually the line of code that your calculator defaults on because it doesn't recognize, because your calculator doesn't always recognize unless you change it into non-real numbers. Okay, that number actually does exist. It deals as part of the non-real number system, which is the complex number system. So you've all heard these before. So the real numbers, this is about everything you've ever dealt with. Rational is anything that can be written as a fraction. Integers. And then irrational numbers are decimals that there is not a fraction that you can make equal. What I mean by that is if I were to say like 0.75, that's the same thing as 3/4. So 0.75 is a rational number because I can write 0.75 to be 3/4 and it's the same thing. Seem okay, sir? All right. I thought I switched. I guess I switched like that. All right. There we go. All right. So use your calculator to find the following. And I'm going to pull up the calculator, and you don't necessarily have to get it out. But I'm going to pull one of the graphing calculators up on my computer. And this works the same as the normal calculators, just it's a larger screen. Allows me to use touch screen on it, which is kind of cool. All right, we don't want any of that. We'll quit out of that, clear this. So if I were to look at I have 4 raised to the 1/2 power. So if I went 4 raised to the 1 divided by 2, I have 4 to the 1/2 power, and it gives me an answer of 2. Okay, let's look a little further. That's not me. 16 to the 1/2, we're going to do the exact same way. So I'm going to go 16 raised to the 1 divided by 2. And I get 4. Okay. And then 36 to the 1/2 power. Let's see, 36 to the 1/2 power gives me an answer of 6. So first thing I think we should look at is for a perfect square. Yeah, because 2 times 2 gives me 4. Is 16 a perfect square? Yeah, because 4 times 4 gives me 16. Is 36 a perfect square? Yes, 6 times 6 gives me 36. So if I'm raising something to the 1/2 power, that means the same idea as taking the square root. So this is equal to 2, but if I wanted to rewrite this, I could write it as the square root of 4. Now, I'm going to put a little tiny 2 right there because that is always there, but we don't default to it. And then this next one is going to be the same thing as the square root of 16. Again, I'll put that little 2 there, which is equal to 4. And then this one is going to be the square root of 36, which is equal to 6. Okay? So when you see an exponent, a power that's raised, and it's the 1/2 power, that means you're taking the square root of the number. So it's changing a radical to an exponent to a radical is all you're doing. Okay, so perfect squares, they're pretty simple. 1 times 1 is 1, and 2 times 2 is 4, and 3 times 3 is 9, 4 times 4 is 16, 5 times 5, 6 times 6, 7 times 7, 8 times 8, 9 times 9, 10 times 10. If you can do that right there, you're pretty much set. If you're a little bit further ahead, that takes it all the way up to 15 times 15. So I'd like you to know all the way up to the red, but if you know just all the way up to the blues right now, you can pretty much get by the rest of this class. Cool? And that's just 1 times 1, or 2 times 2, or 3 times 3, 4 times 4, all the way up to 15 times 15. So those are perfect square numbers. Something that some people might not recognize, there are patterns in math that exist always. If I go 4 minus 1, I get 3. If I go 9, I get 5. I go that minus that, I get 7. I go that minus that, I get 9. That minus that, I get 11, 13, 15, 17, 19. If I subtract the top number from the next bottom number below it, it's all the odd numbers. And you're like, yeah, but what about 1? Well, the first perfect square is 0, so the difference between here and here is 1. So 1, 3, 5, 7, 9. Perfect squares are the odd numbers. That's a pattern that exists. I was like 48 when I learned that. Wait, I'm 48 now. Okay, so I guess I just learned it. Can I move on? Okay. All right, so now it says use your calculator to find 8 to the 1/3 or 27 to the 1/3 or 64 to the 1/3. And I think we might be able to do that, but let's just take a look. So 8 to the 1/3. So I'm going to go 8 raised to the 1 divided by 3. Anyone want to take a shot at what that is? What number times what number times what number gives me 8? 2. Yeah. Okay. And then go back there. 27 to the 1/3. Anyone want to take a shot at what 27 to the 1/3 might be? 3. Cool, because 3 times 3 times 3. And then last one. 64 to the 1/3. Anyone want to take a shot at that? 4. Yeah. Okay, so perfect cubes. So 1's a perfect cube because 1 times 1 times 1. 8's a perfect cube because 2 times 2 times 2. 27 is a perfect cube because 3 times 3 times 3. And so on and so forth. And I'm not asking you to necessarily grab all those, but just know that I have 0 is 0 times 0 times 0. 1 times 1 times 1. 2 times 2 times 2. 3 times 3 times 3. 4 times 4 times 4. 5 times 5 times 5. 6 times 6 times 6. 7 times 7 times 7. 8 times 8 times 8. 9 times 9 times 9. 10 times 10 times 10. I would say know about that. Okay? Now, something that's cool on this, let me do this. New, edit, insert a blank page. 1 to the 3rd equals 1. 2 to the 3rd equals 8. 3 to the 3rd, you don't have a blank page. Okay, ready? We're going to count. 0, agree? 0. And then my last number up here is 1. And then my last number 2, 3, 4, 5, 6, 7, 8, 9, and then 10. So take a look at the last numbers. Anyone have a calculator they have out? Or on your phone? Okay, I would ask you, if you have your phone, do this, or if you have a calculator, do this. Take a 2-digit number, any 2-digit number you want, and multiply times itself. So if we use yours, if you chose 38, I want you to go 38 times 38 times 38. Okay? But what I want you to do is I don't want you to tell me what number you used to multiply itself 3 times. I want you to tell me what your end result is. So has anyone multiplied number times itself 3 times on their calculator? What is your big answer?
13,824.
824, okay. And just remember what you multiply together here in a sec. Who had one as well? Go ahead.
15,625.
625, okay. Anyone else? Yeah?
54,872.
872, you said?
Mm-hmm.
Anybody else? Y'all are going to want to try this right now, though. Watch this. I'm going to split this. I'm going to always have 3 numbers on the right side. Still with me on this adventure? Is that 24 times 24 times 24? Yeah. Yay. This one's 5. 25 times 25 times 25. This one is 8 and 38 times 38 times 38. Come on, someone else do it to me. I just took the cube root of up to a 5-digit number without a calculator. Someone else have one you want to try? Easy. Right. So 2-digit numbers. Don't go in like 11 digits and cube it. Something's got E in it. Huh. Okay. Got something? Big number?
157,464.
Okay, thank you. Yeah?
How'd you get 38 on the bottom?
No. Cube root of 54,872 is 38. Yeah.
884,736.
884,736. Okay. Get it?
140,608.
40,608. Okay. Anybody else? Yeah. 970 what?
299.
Like that? Okay. All right. So I'm going to split. I always want to have 3 on the right side. Whoops, 3 on the right side. All right. So this top one, that's a 4. That's a 54. Is that right? Forgot whose that was. Is that good? Cool. 36, 96, 84, 96.
Yeah.
Is that right? Yay. 608, so that's 2 and 52. Whose was that one? Is that right? And 99. Yes? All right, you want to see how I do it?
Yeah.
It's kind of impressive as someone, dude, you're taking a third root of a 6-digit number in your head. I know. Pretty bitching. Huh? But watch this. Ready? So remember, first something comes in. Remember when I counted the last number? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So the last digit, whatever this is, relates to that last number. Whatever that is relates to that last number. So you look for the 1. The 4, that goes with the 4. That's my last number. Then you find the 157. Well, 157 falls in between these two, right? It's between 125 and 216. So you go to the smaller. So this one, you look for the 6. 6 goes with the 6. My second number is the 6. 884 is between those two numbers. I picked that number, so 96. This one, that goes with the 2, is 8 squared. So the last number. 140 is in between these, so you go to the smaller number, so 54. Yeah.
How did you get the last one in blue? That 2 has nothing to do with the 8.
This one here?
Yeah.
Okay, that 2 is that 8 right there. So that's where the 2 ends. And then the 54 falls between those. So I go with the 38. Yeah.
So basically, you have to memorize all those.
No. That's just kind of a fun little dorky trick that, you can go home, look what I can do. Of course, usually how the story progresses when you get home is, okay, find some number, multiply times itself by 3 times itself number of times. Your parents are like, okay, they take 26 times 29 times 58, and they give you some number, you're like, oh, and you forget how to do it. But it happens. All right, so let's see, 4, I think that says 4 to the 3 over 2 power.
Yeah.
Ooh. And I think this one says 8 to the 2 over 3 power. Agree with both of those? Okay, so this is what I'm going to do. I'm going to look at the denominator. That means I'm doing the square root. So what's the square root of 4? 2. So then I get 2 to the 3rd power, which is 2 times 2 times 2, which is 8. What about this one? What's the 3rd root of 8? What number times what number times what number gives me 8?
2.
2 squared? 4. Done. Or you could have done this. 8 squared, 64. What's the third root of 64? 4. Okay? So the denominator tells you what root. So if I have a raised to the b over c, that can be written as the c root of a to the b. Yeah.
Okay, so for the 8, like how you got 4, so how do you get 2 squared?
Ready? Let's have a fancier color. I'll go orange. Is that all right? If I can get there. Okay. All right. Ready? What is the third root of 8?
2.
2. So because of this, that becomes a 2.
Okay.
But then I'm going to square that. 2 squared is 4.
Oh.
Same thing here. What is the square root of 4? 2. 2 to the third. 2 times 2 times 2. Or I could have went 4 to the third is 64, because 4 times 4 times 4 is 64. And taken the square root of that and gotten 8.
Okay.
Cool? All right, so keeps reversing on. I don't know what I'm doing
Wait,
wrong.
how do you know which one to choose, like the 2 and the 3?
So the top versus the bottom, there's not a right or wrong answer. You can choose either one. Okay? So what we have here is, this is basically our foundation. But let's take a number like let's take 125 to the 2/3 power. Okay? Now, I could go 125 squared and try and figure out the cube root of that, which 125 times 125 is big. Right? Would you agree with me there? But if I looked at it this way, if I said, okay, this means the third root of 125. So what times what times what would you think would give me 125? 25 times 25 is 625.
No, I mean 5 with the third root.
Yeah, so 5 and 5 and 5, right? Okay, so the third root of 125 is 5, and then I have to square that, which, like Oliver said, comes up to 25. Or I could have squared this, could have squared 125. I don't even know what that's going to be. That's it, 10, 12, carry the 1, that's 6, and then I have 0, 5, 250, excuse me. Yeah, if I could do my math, I'd be a much better math teacher. And 125.00, and then I have 5, 2, 16, 15,625. If I take the square root of that, or the cube root of that, I should also get 25. Cool. So a little different way to think about these. Write each expression as a radical. So this is x to the 3 over 2. So I want to make it as a square root. So I will say x is inside. And there's going to be 2 locations we put something. I'll put something right here. I'll put something right here. What do you think I put right here?
3.
3 goes here. What goes here? There he goes. So that's going to be the square root of x to the 3rd. Okay? Is that y to the 1/4?
Yeah.
Is that what it says? So this is going to be, how would I make it here? What goes outside? What goes in the little seat? The 4. Good. And then to the 1st, we could put that. That's fine. I'll totally take that answer. You doing all right? How many more slides I got? 1 more? 2, 3, 8. Get that one? Get that one? I'm done. Yay. Okay. Rewrite each expression as a radical. Classify it as an integer. Okay. A rational number, irrational number, non-real. Okay. So that's going to be 24 to the 1/2 is the same thing as the square root of 24. So can I take the square root of 24 and just get a whole number? Or do you think it's a decimal, like 4 point something, keeps going forever? It's a decimal, keeps going forever. So this is called an irrational number. And I'll just put IRR. Because if I were to take the square root of 24 on my calculator it would go all the way across the screen. It would go 4 point all the way across the screen, however far your calculator would go. And then this one looks like, oh, I have the square root of 2. Square root of 2. If I have the square root of 4, I get 2. If I have the square root of 1, I get 1. So it's somewhere between 1 and 2. But the square root of 2 is also an irrational number. Okay? It's going to be 1.4, and a decimal goes forever. It doesn't stop. So this is to the 1/2 power, which means, hey, I want the square root of a negative. What did I say that was? It's an error. So on your first sheet, what did it say it was? What kind of number? Non-real? Is that one an answer? Non-real? Okay, again, if you do square root of 4 on your calculator, it doesn't work. What about this one? I think that's going to be square root of 16. What's the square root of 16? 4. That's a nice sturdy number. There's nothing there, so that's an integer. Okay? And then this, the third root of 8. Ooh, the third root of 8 raised to the first. What's the third root of 8? 2. That's a nice one. That's got to be an integer as well. Oh, man, are you kidding? I got a fraction raised to a fraction. I already didn't like fractions. Now you're going to raise a fraction to a fraction. What are you doing to me? Okay, well, this is the same thing as the square root of 4 over 25. What's the square root of 4?
2.
2. What's the square root of 5?
1.5. Oh,
5?
oh, no.
So 2 over 5. Oh, that's a nice fraction. I can write it as a fraction, so that means it's a rational number. Okay, rational numbers can be written as fractions. That's pretty straightforward. All right, so if you have two rational numbers, will their sum be a rational number? Okay, so if I have a rational number, so 2 over 5 is a rational number. And if I have another rational number, 1 over 4, that's also a rational number. Agreed? So if I add these together, does my answer come out to still be a fraction? Can I add two fractions together and get a fraction for an answer? Yes or no? I think so. I mean, that's going to give me 8 plus 5 over 20, so I get 13 over 20. Is that a fraction? It looks like it. So if I have two rational numbers, will their sum be a rational number? Check. Okay, I can't think of a situation that won't happen. If I have two irrational numbers, will their product? If I have two irrational numbers. Ooh, irrational was what? So an irrational number would be like the square root of 2 is irrational. And if I wanted to multiply the square root of 2 times, say, the square root of 3, square root of 2, decimal goes on forever, never repeats. Square root of 3, decimal goes on forever, never repeats. If I multiply these together, I get square root of 6. Is square root of 6 a perfect square? So if I multiply two irrational numbers together, if I multiply them together, can I get an irrational number out? Yeah, that's irrational, that's irrational, that's irrational. I don't think we got lucky finding the only irrational that worked. Okay, so an irrational number is a radical that can be, when you make it a decimal, it goes on forever. It never repeats. Okay, so this is solving quadratic. Where is this one? Where am I at? Solving. What unit am I on? We graphed them already, right? Yeah, we did. Solving quadratic functions. So I think your homework, it's going to be page 99 and 100, but you'll find something pretty cool about page 100. What do you think that would be?
Blank.
It's blank, yeah.